like I have to get my. It's like a make morning.
Okay, so thanks much for
That's a good.
coming and keeping investing your time into the course.
I just sat through 2 hours of CCAS training. I'm ready to go.
Oh, good, good. Then I need to add special topic. Did anyone told how to open CCAS account last time? Did everyone follow it? So someone needs to, or maybe several, share experience in opening CCAS and running Gaussian on CCAS.
Okay.
Like right now?
Cast. So the main goal of the meeting today is to fill this table. Of course, I'm lying, or I'm not lying. It is not the only goal, but maybe the most important. So there is one this black star. I should put the diamond as for downhill skiing. And another subject, so please distribute your names, whatever you feel more comfortable to present in 2 weeks, right? Mostly it is what we already covered in the labs, but if not, last time everyone was so good in bringing new topics. And I'll distribute a couple more copies for just for your information, so you may record what you like to do. You may spend a little time in deciding, thinking.
Thank you. What does the red mean?
I don't know. Can we start giving a question on it? So I'll show this page on the screen and we'll discuss it more. So who we are and what are we doing? This meeting will be most useless of the whole course. So if you're coming here to lean back and relax, it is the very time for this. The whole meeting. So we will do a little review of what we did before, of our goals and plans, but most of the meeting I will try my best to remind about concept of a spin, which is will make, if you sit and carefully participate, it will make you happy, it will bring you intellectual satisfaction, but it will not bring you much closer to doing practical computations. It's just some of you may already have a lot of background, some may have some gaps, and we make sure that everyone is on the same page to speak about multi-electron wave functions. Okay, so I promised the homework, and I will probably distribute it by email, most interesting part, and I will distribute a portion of the homework which will be like pen and paper little thing based on today's meeting. Maybe I'll distribute it right now, and then you will have a little more, how to say, I don't want to irritate anyone to say interest to equations, but logical connection. You will parse material from the lecture and tell, will it help me to do this little assignment or not?
So is this one due in 2 weeks?
Well, existing one to you. Because he gave us.
Let's plan. I will remind all details about assignments, but let's plan in a week.
Okay.
On Tuesday. Just it's easier because I will be using records from previous years, which are split by weeks. If we accumulate everything in
So do it on the 19th then?
no 19th, yes 19th. And since I will be not here, you may consider to like scan and email, right? So this one is really easy, and if you know the answer for each of them, then there is nothing to do for you in the class today. Okay, I'll start.
Is alpha up and beta down?
Yeah. So again, who we are and what are we doing? We are in the computational chemistry class. Our goal is, what is our goal? Our goal is to characterize properties of materials, right? Answer? Yes. Good. And we are in the chapter for Hartree-Fock theory. So before we covered some aspects related to nuclear degrees of freedom and separating electronic nuclear degrees of freedom, and which is important for molecular dynamics and optimization. And now we are doing the first approach to go over electronic structure, finding electronic states. And we covered Slater determinant. I'm going to review it again. And before we will go to philosophy, Hartree-Fock theory, and machinery, how it works, it would be really reasonable to refresh our memories about spin, which many of you had in one or other aspect, like basic quantum theory, or some of you did operated NMR instrument, and we need a little bit of it for electronic structure and Hartree-Fock theory. So this is about where we ended last time, right? So what is it?
Determine.
Yes, we need to product of diagonals, subtract product of diagonals. And this is a way how we construct multi-electron functions, wave function, of single electron wave function. So the reason for this little crazy construction was twofold. First, that truly multi-electron functions have too many arguments and we do not have computational power to store and process them. And second, that we should follow the testament of Pauli to forbid two electrons to sit in the same quantum state. And if we try to sit on two chairs, on one hand to separate variables and make a product, and on another hand to satisfy Pauli exclusion principle, we will want to form combinations of this way. So here the F and G are examples of different orthogonal eigenfunctions, electronic functions, and R1 and R2 are positions of first and second electron. Oh, we all know that Born-Oppenheimer separation. let's keep it. It's plans for some homeworks and reports, and we were while looking on electronic properties, we've forgotten to focus on the geometry, which later on we may need to focus. I'll try to minimize this part of assignments, but in your practical works, sometimes if you optimize a structure, you may need to report interatomic distances, angles, if you want to compare with what comes from X-ray diffraction or from other calculations. Okay, so here is the list that you are about to complete filling, and we have covered about starting from here. So how to run Gauss view and how to process outcome, right? So photon energy, ionization, electron affinity, we covered, right? If you didn't, you will in the lectures and both labs. We went over Perl scripts for density of states, numerical data, density of states. We did start molecular orbitals, right? That's what we did last night, but and isosurfaces. But we didn't cover open shell configuration. Exactly the subject that we are starting to touch today, when the number of spin up and spin down electrons is different. It's not a big intrigue. In the keyword for cube gen, you just add the uppercase A or B, like A, MO or B, MO, and then it will draw the alpha and beta molecular orbitals. So, you may know what is it. If you don't, we either cover or someone
I forgot.
We'll cover. It's just distribution of charge near these elements. Like which one is oxidized, which is reduced. And we didn't cover, but those things are, on one hand, they're trivial, on another, they're really important. So at least several, we really need someone to cover this aspect. So how to prepare input of the Gaussian job file if you do not have Gauss view. How to do it in command line.
All for CCast or just?
Not the PBS script,
Okay.
but the actual .com or GJF. And
List is done.
well, there are a couple of people who are not here.
I picked the
Probably.
mulligan.
Oh,
No. It's lonely.
So no one selected my favorite one, but either I need to present or maybe someone will decide. So if there are chemical chemists in the audience, it is most chemical part. So scan of potential energy surfaces for reactions, and it could be used for reactions. I saw this first three were already selected, so okay, we'll talk more about it. Oh, this is previous year. So with years I should redo this figure, but it is a flow chart, logical flow chart of how to compute electronic structure with Hartree-Fock. So there are several key elements, and don't listen, we will cover it later. So we covered Slater determinant, and then there will be concept of mean field, exchange, correlation, and this all can be done with help of spin concept that we are covering today. In some sense, remember the functional form of Slater determinant, right? For two electrons. And no one was arguing, and we kind of not proved but displayed that if one would attempt to place two electrons into the same quantum state, Slater determinant will prevent us, forbid us to do so. It will give 0. But how to get this functional form? We showed that it is good, but where it may come from? How to? Is there any mathematical protocol that will form such antisymmetric combinations? Again, this will be not very rigorous path, but if one considers several spins, system with like 2 spins, the antisymmetric solution is one of the natural things that come out from concept of spin. So it's not literally logical way to define Slater determinant, but it kind of complements the picture and helps us to feel more comfortable with it. Electronic, kinetic, electron repulsion, electron nuclear attraction. And this solution wave function can be composed as Slater determinant of several 1 electron orbitals. And if you have more than 2, we can arrange this matrix as in each row we list orbitals, like eigenstates, first, second, third, and in as we go down through the column, we list electrons, first, second, third, and then practice standard rule to finding determinant. We are not covering it here, but in linear algebra, some of you took it, some of you plan to take. There are rules that it's almost on the first lecture of linear algebra.
I'll do number 4 if you want me to, as well.
You write down like second choice. Thank you. So I should put the microphone off here. I will tell you something theoretical. That please listen and think about it, but never speak it in public. Okay? So it's only a little concept for connecting things around. But again, never repeat it. So spin is a rotation of electron around itself, either to the left or to the right. Okay? So it can rotate with constant speed in clockwise or counterclockwise. If it rotates one side, it's spin up. If it rotates it downside, it's spin down. Again, it is wrong. Do not repeat it in public. It's only to get some ideas, to connect something. Okay? So it's not rigorously it is wrong, but it navigates our minds in the right direction. In the following sense: if the charged object is rotating, then there is a current, and current creates magnetic field and interacts with another magnetic field, right? Or if a charge is moving, there is a angular momentum. If anything, a mass is moving, there is angular momentum. Then we multiply it by charge, and it helps us to assess how much this object will interact with magnetic field. And from this point of view, a rotating sphere, like if electron has a radius, which is also nonsense, and it has speed of rotation, then it would have magnetic momentum, angular momentum, one or another way. Do not tell it. The only thing that we are allowed to tell is that there is a quantum number corresponding to angular momentum of speed, which takes 2 values. Okay?
So quantum number.
The value of angular momentum or magnetic momentum corresponding to stuff that we are not going to pronounce,
Okay.
can take only discrete values, as anything in the quantum world, right? It's not any value, but only discrete values. Plus 1/2 of Planck constant minus 1/2 Planck constant. So here it is, rotating thing, but it's not for the public. It's only between us. So I see some laughing faces. Those who take physics for serious may have considered it, may have solved the problem, like what should be the speed at the surface of electron if it has a radius, if it rotates to create sufficient momentum, and then the speed on the surface of electron should be much more than the speed of light, so it will break our understanding of the world. So we shouldn't speak this way. Only to connect things. What else?
So it's the quantum number corresponding to the value of angular momentum.
Yes,
Okay.
intrinsic angular momentum of a spin.
So this, when you read it in the books, this is how they're going to refer to it.
Yes.
Okay.
Yes, and if one is looking for our building, again, maybe I will change my mind and confess a little lie later, but right now, atomic orbitals are our building blocks, and Slater determinant is our blueprint. Right? So our building blocks are atomic orbitals, which may, as you saw yesterday, which can be centered on different atoms. And they are specified by, last time in class we mentioned 3 quantum numbers: principal, orbital, magnetic, but there is one more, spin, right? So for if we draw these orbitals, on each orbital there could be two electrons. One with spin quantum number +1/2 or plus h bar over 2, and another with minus h bar over 2.
Is that just spin up, spin down?
Spin up, spin
Yeah.
down, yes. That's- So it's additional number to label atomic orbitals. Clearly presented label, because different people name chemical structures in different formats. So you can understand from human nature that molecules can be encoded in different styles of files, but even such simple thing as spin has variety of ways to encode and to represent in writing. So some people tell it is spin plus, spin minus, some tell that it is spin up, spin down, some tell that it is 0 and 1, some tells that it is alpha and beta. It's a matter of convention. Okay? Do not be surprised either one.
So when you go to a conference, just keep that in your wallet so you know.
Yeah, addiction.
A little key, keep it.
Yes. So what else do we do with spins? Well, there are 2 eigenstates, 2 quantum states, but a certain given electron can be placed either in one state, another one, or can reside in superposition, right? If you were exposed to quantum theory, it's not a new thing for you, right? One can be like 50% in one state, 50% in another. So we may overview like basic mathematical tools to process this concept, and slightly connected to the things that we are doing in class. Again, entertainment. Back. It's I do not remember referring or using it to anything except this little assignment. It's only conceptual. So if we are kids sitting in a sandbox, having a set of toys that we want to break because it is our pleasure, right? So if you have something, you need to want how you can operate with it. And if you have spin up and you're a kid, your natural wish is try to flip it over. But we are trying to project things more in a mathematical way. So if we want to flip spin, we need to spin flip operator, right? By the way, do you feel comfortable with this angular brackets? Everyone?
What is it?
Okay, in a couple of slides I will reintroduce it. So, and I will reintroduce this stuff also. So if you want to flip it from alpha to beta, we just make this flip operator. So a couple of years ago, I was delivering this material to students of another year, and later on, there are rumors, there is like word of mouth processed in an unknown direction, and I've heard back a feedback about this meeting. So like the feedback, I understood nothing, but it was something crazy about birds. So prepare, you'll see birds today. And maybe it is the only thing that you remember after years. So a little definition. So if you do have a wave function, right? Sometimes you may want to the natural. Well, I know it's wave function is not natural, but if you already have it, there are a couple of natural wishes to do with it. One natural wish to check if it is normalized, and second one is to find expectation value of some observable. So for normalization, you just multiply wave function conjugated to itself and then integrate over your space, if it is position dependent, right? But if it is, if your wave function is defined not in the continuous space but in discrete space, then this operation is replaced by a scalar product of vectors in the right space. So there is ambiguity. Wave function can be continuous, can be discrete. Normalization once uses integration, another time it uses scalar products. Is there something more general, unifying, to tell like normalization of wave function? We will have specific math symbol that will work for any argument, for any variable wave function depends on, either continuous or discrete. So these angular brackets or Dirac notations are designed to take into account this property. So if you write usual wave function, say, it corresponds to right angle. If you do conjugation, it corresponds to left bracket. Again, if it is, I do not put it here, if it is column vector, it is right. If it is row vector, it is left. And the product of two conjugated and non-conjugated wave function is represented as left times right. And the left and right are called bra and cat, because you write bracket or bracket and then split it on two. Right? So left is bra, right is cat. So if you have two wave functions and do bra and cat, it will be a number. You can convolute your wave function into a number. For example, you find normalization. But mathematically, you can swap them and make cat times bra. So order. And then it will be operator that converts wave function from one state to another. If you were exposed to quantum theory, you like really relax and nothing new. If you were not, it may sound counterintuitive. Prepare for birds. Oh, suppose you have a bird. Owl. And you have an operator that tells like skylark. You see connection, spin down, spin up. And operator that converts.
Yeah.
Okay? Intuitive, no objections, simple. So let's write it down in quantum language. So there was a quantum state, like I am in the all state, which I'm sleeping. Then there is an operator that converts me into skylark state. Okay? Both of them are cat. Agreed, right? What else can we do with these images? We should use the idea and explore it in more details. So, if we prepare conjugated bra of the all and convolute bra all with cat all, you get one. Right? Overlap of the, like if you take normalized function, multiply it by itself, integrate, it will be one.
Mm-hmm.
Like identity.
Oh god, I was gonna say that. That's what I was thinking.
Identity. But if we take, well, if you take Skylark with itself, it will be also identity. But if it will be different objects, they do not overlap. They do not coincide. So their overlap is 0. It's Dirac notation, although I never saw Dirac drawing birds. Okay? What else? So we considered bra and cat when they angle by flat stuff to each other and angles outside. But we can swap them. You can swap the order and consider instead of bra times cat, you can do cat times bra on the same bird's language. So if you formulate cat times bra, but both cat and bra will be all, it will be, well, like cat times bra is always an operator. But this one is projection. If I do not know if I'm sleepy or about to wake up, I don't know if I'm all or Skylark, this operator applied to me will project me onto the all state. Right? So it will, I'm missing Kurt on today's meeting, but if we all are exposed to computer science, you know, you can have text and then parsing right portion of a text out of it. Or like in Linux command grep something. So one can parse all component of myself or of the quantum state. Projection, parsing. Okay? And if cat and bra have different objects here, it means convert. So if this one will be applied to an all, it will convert it into Skylark. If this will be applied to Skylark, it will be 0. Because all as bra times cat as Skylark is 0. They do not overlap.
So this.
Should we distribute more coffee?
No. So the previous one was parsed, and this one is. Not.
Oh, Kurt! Happy to see you. Were you following things? Or you just...
Mostly.
Okay.
Well,
Yeah.
Good. So we
I
were.
said
Yeah.
I said the video and audio muted, so I've been following along.
Okay. Then you may turn the microphone off, but if you want to ask a question, then put it on.
Okay.
Okay. So we were mentioning you, but only in a good sense. Okay. So.
So the previous one was parse. This one is not. You said it was a special.
Okay.
Convert.
Convert. There we go.
So this is wave function.
Okay.
This is a wizard.
Okay.
So that converts all into a Skylark. And right now we look on this object the following way. Here is our wave function, here is our operator. Right? But if we just play logically with like maybe cards on the table, we have 3 objects. Cat, bra, and another cat. And no one told us that we need to circle or highlight this one first. We may cover by rectangular frame these two first, right? So if we cover these two things with a frame, so we need to recall this is convolution, which will be 1 if they coincide. They do coincide. So this stuff is replaced by 1 identity. And then we can remove it completely. Because multiplying by 1 is meaning like keeping identity. And if you remove it completely, we are left with skylark. So it is a mechanics how wizard converts an all into a skylark. Quantum mechanics. Maybe one day I wrote it, but I do not speak this language typically. It's easier just to deal with figures. So it's an abstract mathematical tool. Good? Mm-hmm. So, do you see any connection to little assignment that you got? Alpha and beta are your skylark and all. Right? And we should speak about either projection or like this wizard conversion operator. So the S plus operator that will convert alpha into beta. So alpha, and here the cat and bra. So if you look on them together, alpha and alpha convolute and form 1, and we are getting beta. Make sense? Oh, it is written here. So S plus acting on alpha gives beta. Complete.
I have a question.
Please.
In the homework, are we supposed to have little ones next to these guys? Are they?
No, your homework is a little easier. So
okay.
Let me. We are speaking too long. Well, I'm speaking too long. You are speaking. So let's recall what is the goal, who we are, and what are we doing. We are computational chemists. We want to characterize properties of materials. In narrow sense, we are solving Schrödinger equation that depends on positions of ions and electrons. We kicked out ions, and we now solve only for electronic wave function. And electronic wave function is represented as Slater determinant of atomic functions. There will be some addition to this. It's not the whole truth. And we need to get some background. What is the origin for antisymmetric wave function? Is there a way to where it's coming from? On one hand. On the other hand, we just need to get acquainted a little bit more with spin generally, especially those of us who will deal with open shell objects. For example, transition metal complexes in crazy oxidation states. Okay. So your question about number 1. Mm-hmm. This is intentional. I'm going to bring in 2 spins. Two electrons, each of which has a spin, like spin, first spin and second spin. In each of them can be alpha and beta. Okay. And therefore, we need this number 1, and there will be another with number 2.
Okay, got it.
Okay? Okay. It is too much of writing and concentration for homework, so it will be not there. But here, I'll try to entertain you, if you consider it as entertainment. Well, you already got birds. you remember something.
What is Skylar from? Is that from a kids show or a movie or?
I don't know.
Yeah. Okay, all right.
Just something that one can remember.
Okay.
So, what is the opposite to plus?
Right.
Okay, so if we have a spin conversion from alpha to beta, we should have a conversion from beta to alpha. And we form it in the opposite way. So if it convolute with beta, it will create alpha. If it will convolute with alpha, it will create nothing. So, by the way, operators with minus sign can be called annihilation, because you are going like down, and plus creation, because you like create, spin up. So if we act with this beta alpha operator on alpha, we move our frame with our focus from these two things onto these two things, and we see that they do not coincide, which means their Bryan cat product will be 0, right? Means 0 that it will be nothing. So trying to annihilate spin down will give you nothing. You cannot annihilate vacuum.
So you're saying annealing?
Not annealing, annihilation.
Okay, got it.
There are two words. Annealing is like heating and slowly cooling,
Yeah, that was what I was
and annihilation like
Completely.
yes,
What?
completely destroy.
Ah. Oh, annihilation.
Yes.
Yeah, sorry.
Yeah, it's so nice to participate in educational activity because it helps to learn right pronunciation.
Okay.
So, and if you try to apply this S minus operator to spin beta, to spin up, we'll do it again. So it is beta times alpha, cat and Bryan, applied to beta, and then we move our focus to this frame, and we see beta and beta convolute and get 1, and as a result you get alpha. So applying S minus to beta, we are getting alpha. So if you are up, we are getting down. If you are down, we get nothing. Similar idea as we get on Tuesday. If you try to put 2 electrons into one state, you just get nothing. So there are some ways to prevent us from doing bad things. Or wrong things. So, superposition. Given single electron can have spin up, can have spin down, or can be in between. Superposition, 50% here, 50% there. Maybe different. 51 and 49. How does it record it on math language? So it is sigma, quantum state of a spin, is alpha plus beta, with some expansion coefficients, which are chosen to give 1. Like if one of them is 1, another 0, you get 1. If it is opposite, it still get 1. If each of these coefficients like 1 over square root of 2, it will be 1/2 plus 1/2 will be 1 again. Right? So generally, spin wave function of electron consists of 2 terms, and recording is recorded with 2 expansion coefficients. Right? So generally, these operators that we start to introduce should act on general wave functions, which may have a little bit of those and a little bit of those. So, if we do not know values of these coefficients, what is the probability that we have spin up? Just by definition, probability is wave function squared. Right? So we have C sub beta squared. So the probability that electron is in state up in beta. Right? So it's intuitive. But is there a mathematical procedure that will give us this answer? Is there a mathematical procedure that intentionally designed to parse this C sub beta star C sub beta out of this wave function. We already covered the answer. You know the answer. So this one, S minus, means flip down. This one, flip up.
Mm-hmm.
So if you subsequently flip down and then flip up, then we will see. So here is the beta that we
So
will see.
can we treat it like a matrix?
We will go to the matrix. We will go to the matrix
Okay.
very soon.
Okay.
And I hope I will not expire your patience.
Okay.
So for S minus, it is beta times alpha. For S plus, it is alpha times beta. Now we can focus on the central part. Alpha times alpha, which convolute and give 1. And we remove it. And we get beta bra and beta cat, which will be a projection of quantum state on the state up. And if we design this projection operator correctly, then expectation value of this operator should give us this value.
Could you explain the expectation value a little bit more? A little background of it?
Absolutely. It's a
Okay.
great pleasure. Let me do a little survey. Who is happy about the concept of expectation value? Who is very happy, very confident? Who is very uncomfortable? Who is in the middle, who have heard but not quite? Okay, good. Thank you. Thank you very much for asking. So it's not a goal of a course, but it is a really important portion of background information that can be useful for all of us. So I apologize for repeating some background simple things again and again. So we are in computational chemistry course. Our goal is to characterize properties of molecules and materials. And properties in the more scientific and rigorous sense is what is coming out from instrument, what is being observed, right? You measure cyclic voltammetry in analytical chemistry, you measure color in optics, which either absorbs or emits, you measure conductivity, right? So always it is a property, and then you provide it with number, right? Observable number. In classical theory, it was variable, for which you write equation. But in quantum theory, you do not have variables, you have only wave functions. So the expectation value is a procedure to extract the value of observable that you will find if you do analogous experiment to our calculation from some computational procedure. So it's a way to find most expected value of some observable.
Could be any observable.
Well, if you know how to design the operator. And mechanically I mean like protocol for computations. Expectation value is bra and cat of operator of your observable. So if you have observable for absorption, you put it inside and you put wave function of your molecule at the left and right, bra and cat. As a result, you will get, well, not immediately observable, but withdraw last sentence.
Okay, so really it's a mathematical concept.
Mathematical concept
that we apply
of converting wave function and operator into a number that can be measured on experiment.
Okay.
And finding expectation value. Is it reasonable to those who other alternative definitions?
Well, yeah, alpha and beta. Well, those are wave functions that we would have gotten from the previous equations that we've dealt with.
Wave function is sigma.
Oh, okay. So
Alpha and beta are basis states.
basis. Okay.
Basis states. Whew. Oh, we already covered it. So now we are going to find if the expectation value of the operator that we have designed will give us C sub beta squared. If it will give us probability that electron is in the state spin up beta. And with this purpose, we will immediately, many thanks for asking this question, we will immediately practice the procedure for finding expectation value of this operator. I do not know, well, maybe I know, maybe you know what is spin up and what is observable. Maybe it's some like magnetic field splitting Stern-Gerlach experiment, but right now more mathematically we just build construction and put bra and cat wave function to the left and right. Okay?
I have a question.
Please.
So when you were going to spin up and spin down and you explained that point where we get 0 when it's down, this relates to the observable? Because we look at, like if we try, is it hard to go from up to down and then down to up, or we just can't, once we're in the down position, it's like, well, we really can't go the other direction.
So what I'm trying to present right now is a little departed from true life. There are experiments that measure spin. There are experiments that flip the spin.
Mm-hmm.
But right now, if we will start speaking about them, it will be a little too long. So we are taking most of the mathematical aspect to stay within time.
Okay.
Okay. By the way, there is a portion of basic quantum theory courses that start from spin, rather than continuous wave functions. I don't know if people like it or not. Maybe it's not the right idea, but mathematically, well, for human level of how counterintuitive it is, it's not very intuitive. But mathematically, it is the simplest possible concept in quantum theory. So, what are we doing? We are following this protocol. Here we will plug in our bra and cat, our operator, projection operator, and here we will plug the bra and cat for wave function. So this is a procedure to find expectation value of this operator for this wave function. And you see, if we convert from cat to bra, we flip the direction of the angular bracket. We flip direction of the angular bracket for basis state, and we put a little star, which means, do you know what is star for a number mathematically? Huh? So, what is a conjugate of imaginary unit?
Complex.
So, please solve a little problem for me. What is a conjugate of imaginary unit of I?
Is it a negative?
R becomes negative.
Yes, yes, minus I. What is the conjugate of 1? Real 1. 1. Okay, so real part gets untouched and imaginary part flips the same. Okay. So now I'm going to plug in this portion here, this portion there, this portion here. Right? So bra, cat, and operator. Expectation value of projection operator. Make sense? So, for next 5-10 minutes, you do not need any knowledge in quantum theory. It's a pure mid-school algebra. just opening brackets, right? So if here is one term, here are two terms, here are two terms, what will be the total number of terms after we open the brackets? 2 times 2 times 1, 4, right? And if you need to, you can practice it, right? Just opening brackets. So there are two ways to approach it. One way is to open brackets first and then process each term, and another one is just to look on terms immediately. Maybe I'll open the brackets. Otherwise, it will be boring. I feel guilty that I didn't write anything, just showing slides. So first term will be C star alpha S plus S minus alpha C alpha, right? So this and this. Second will be C star alpha C without star beta alpha S alpha S plus S minus beta plus C star beta C alpha beta S plus S minus alpha. And the fourth one, C star beta C beta beta S plus S minus beta. Right? No objections. Just taken first and second, second and first, second and second. And now these products of expansion coefficients are just numbers, and this bra operator cat are something quantum that we may want to open based on our previous consideration, based on birds. Right? And if we do everything correctly, then first, second, and third terms should give zeros, and the last one should give 1. So the right answer should be C star beta times C beta. So probability that electron is in up state should be C sub beta squared, right? So if we do everything right, this and this should get 0. Are we getting it? Can you get it? I think so.
So the C star alpha is down. Spin down.
So I'll process it for with each term. So here we have beta alpha alpha C star alpha C alpha. Here we have alpha beta beta C star alpha C beta C star C alpha beta alpha C beta star C star beta beta. Oh, you do not see it, and I do not know how to remove this little screen.
But you'll post the slides with.
I will.
Yeah, okay.
But it's a completely different thing, participating actively and watching.
Well, yeah, yeah. So is this taught in Hirschberger's class then?
I do not know.
Okay.
I never sit in there.
Because that's the quantum That's the quantum theory class, right? This is
It,
where
it,
they...
it is, this material is very appropriate for
Okay,
quantum theory
okay.
class. So let's look at least you see the first term. I've heard some giggling, but I didn't when I was excited writing, but I didn't realize that is because you couldn't see it here. So this is our projection operator, right? But now we can focus on on this little part. So alpha and beta do not coincide. Their convolution will give 0, and here it will be also 0. So the first term goes out, right? Here it will be beta, beta, it is 1, it is good, but here is alpha times beta, again 0. So second term goes out. There it will be beta, beta, and here it will be beta, alpha. This one will be also 0. So the first three terms go out. And in last one, there is a convolution beta and beta, which gives 1, and here beta and beta once again.
So 1 and 1 and then the 2
Yes.
difference. Okay.
Yes. Ah, I shouldn't spend my time on.
No, it's good. That's
this. Okay, it is what I was writing. So here convolution is 0, here convolution is 0, here at least one convolution is 0, and here both are 1s. 1, 1, and those are zeros, right? So 1 times 1 is 1, and the answer is C sub beta star C sub beta, what we expected to get. So projection of quantum state of spin onto state up. So we, not much sense, it is more like tossing and playing mathematically with evident things, but later on these protocols can be applied to more complicated things where intuitive thinking doesn't help.
So I thought the first one was 1, but it's not.
No.
Okay, so the
come,
the first never
come
mind.
and show.
Oh no.
So
Okay.
you need to see opposite brackets,
Okay.
left times right.
Right.
And if here will be the same symbol, it will be 1, but it is different.
Well, right. Okay.
What is the same symbol? It would be 1. If
Like see,
alpha,
here,
alpha, beta,
beta and
yeah.
beta gives 1,
Yep.
but beta and alpha gives 0.
And yep, we have to look at opposite sides. We can't look at the two betas in the middle.
No, because
That's where I was getting
because they
at.
face this. This is like not convolution, but dyadic product that gives operator.
That's what I was missing out. Okay.
Okay. So you are doing good. We designed an operator that gives us projection, that gives answer. What is the probability to find electron in state up? Yeah. So there is a little thing that likely will not help anything. The whole lecture is irrelevant. And the most irrelevant part that I'm going to draw probably here. So please give me signs if you were exposed to NMR experiment or if you read about it, if it is not a new thing for you. Okay, give signs if you never read and never played with NMR experiment. Okay, so a lot of molecules have unpaired spins of different nature. Proton spin from nuclei, right? And spin can be either made to rotate or flip by electromagnetic field in radio frequency. Not optical frequency, but radio frequency. What's the number of megahertz for typical NMR instruments? If you look for instrument they typically break, we have
It's pretty high.
400 megahertz.
Yeah.
So it's a typical radio frequency that operates to flip nuclear spin. And the spin is a measure how much the object follows magnetic field, how much it interacts with magnetic field. Right?
NMR stands for
Nuclear magnetic resonance. So the connection works in the opposite direction. If you have a system with many unpaired spins added together, it will have substantial magnetic moment. And it will create, like, if you have your compass, it has a lot of unpaired spins, any magnetic material. So in some sense, the spin and magnetic field are connected. And if you make an average over big chunk of over ensemble of molecules or large piece of matter, magnetic field, magnetization, is a regular three-dimensional Cartesian vector with three components. Right? So there are ways to, please be patient. All other lectures will be much more interesting and relevant.
Well, question.
Please.
Wait, so unpaired spins, so say you have some in your d orbitals. We were looking at the p table the other day, say we had some unpaired spins. The electric field,
Electric or magnetic?
the magnetic field will respond to those, or those free spins will respond.
Let's collect many unpaired spin metal
Okay.
atoms together and form bulk iron.
Okay.
And then we add together all the spins and find that iron is magnetic.
Yes.
Okay? And magnetization is a vector with three components. So there are ways, I'm not covering everything, but there are ways to connect these spin projections and three-dimensional vectors. Okay?
Does that, sorry, no. Was that relating to Fatmida's, what she was showing in her poster in some way?
No.
Not quite.
No,
No.
not quite.
Okay. Okay. I was trying to see, because it's been a little time for me. Oh, okay.
So, did you get the last idea? So, connection between spin projections, which are complex numbers, as everything in quantum theory, and real three-dimensional vectors showing orientation in space.
Okay.
So, if you consider the following combination. Yes, cancel. X minus y. So if you consider this combination and then you add and subtract these two lines, you'll see how X projection is combined as summation of S plus and S minus operator. Y projection will be subtraction of S y and S minus. Okay? So those are operators, but taking expectation values of operators, one can get observables. Again, these operators are only for single spin, but if you, after this expectation value, you also make average over ensemble, then one can get magnetization, projections of magnetization. So one can get from our operators that relates to like owls and skylarks, one can get to three-dimensional projections of magnetization. And here I'm showing way towards X and Y, and there is a special operator for Z projection.
Question.
Yes.
With the computational methods that we're learning, the projections, can we visually see that? Have we visually seen it?
I've got the question, I have the answer. It is possible to see, but most, you will see it very soon, maybe in today's slides. most calculations, practical calculations that are easy to complete and are requested by collaborators, neglect superpositional states. They accept that all spins are either up or down, no superposition.
Why?
It is because it is so much cheaper to compute.
Okay.
There are special keys in codes that allow this arbitrary direction of spin, what you want to see, and it is called non-collinear spin calculations. They are quite exotic. Most of people try to avoid them because they are like substantially heavier in practical computations. But it is possible.
Visually, can you get a graph?
Oh yes, yes. You do hedgehogs.
Hedgehogs?
Yes.
Okay.
When you do regular orbitals, you have density,
Right.
in each space. But if you have 3 projections, then in each point of space you draw a little needle,
Oh,
and
so
then
it'd be-
and then you draw a hedgehog.
Really?
Hedgehog
Okay.
orbital.
Wow. Okay. Do people represent it that way then?
Rarely, because it is more expensive to compute.
Okay. Okay. That's if you want to be fancy, I guess.
If you're ready to pay for being fancy.
Okay.
Okay. So I think we are about to complete. So what do we do this time? Yeah, we will be we will be complete soon, like 4 or 5 slides. So let's summarize. So I do have two things to complete. First, conversion of everything we told into matrix form. That Murray has had a vision that it will be matrix form. Prompted. And second, how to get from all these dirty games with spins, which I see on your faces that you are tired and irritated. Would it ever help to build functional form of Slater determinant? So I will pave a way as a little overview. So first, matrix representation. Again, what we are doing is not literally used in the course and in practical computations, but it will set up. Oh, you see a shadow instead of me.
Okay. It's good. Nice.
Well, we need to cheer up this boring material somehow.
No. No. So, but this is the material that you talk about if you're going to put a poster together. Like you want to talk about this kind of background, right? A bit, or kind of at least it's going to lead to that.
If you do posters, there is no space for all background, but
No.
you need to have some background connection in your head to be able to answer questions.
Right.
Okay.
Will somebody ask a question about this?
Yes. Yes. So let's wrap it up.
Okay.
To have a quick. You have noticed that spin has 2 states, and there are just 2 expansion coefficients, C sub alpha, C sub beta. So we can consider spin quantum state as a vector of 2 elements. Well, like in real space we have 3-dimensional vectors. On a plane we have 2-dimensional vectors. And spin is 2-dimensional vector with a little specifics. Each of the component can be complex. So it's not really visible by humans. So then the eigen state alpha can be recorded as, so vectors are just 2 numbers, right?
Yep.
If we go from cat to a bra, then we change column to a row, right? If we do have the general spin vector, which can be either in alpha or beta. I'm not showing it here, but beta will be, number 1 will be in the 2nd place, right? So 2 basis vectors. either 1, 0 and 0, 1. Complete basis set for the simplest problem. Now, if we do have a general vector, this one, then we can say it C sub alpha times 1, 0 plus C sub beta 0, 1. Right? Linear algebra.
Yep.
Yep. Vector as a superposition of basis vectors. If we go from bra to cat, if we do just conjugation, then we have C star alpha times 1, 0 vector, row vector, plus C star beta, yeah, 0, 1, right? Changing from row to a column. Now, how would we, like, if quantum state is a vector, then operator is a matrix, right? So we need to build a matrix that would correspond to raising and lowering operator, right? So raising operator should convert state 1, 0 into state 0, 1. So it should be something that acting on 1, 0 will give 0, 1.
Okay.
So if you multiply row by column, this matrix by this vector, row by column will give first element 0, and second row by column will give 1. So by multiplying this matrix by this vector, 1, 0, you will get vector 0, 1. You see it, right? Then the lowering operator, it will be again 2 by 2 matrix, where 1 will be placed in the upper right position. Okay, so quantum mechanics is just application of linear algebra, nothing else. Okay, I didn't lie. So you do have a dictionary. This is this is a dictionary, and if you do see the this little assignment for the homework, you just practice it either in direct notation or in the matrix notation and get answers. It's really, really quick. I think some of you will have already completed, or you may have completed it like 3 minutes. Okay, and the last thing, probably I can put it in just by going over one slide. So suppose that we have 2 spins rather than 1. I will not solve this problem. I will only guide the way and make things logically connected. So if we have 2 spins, we can label them sigma 1, sigma 2. And quantum state of first spin, it will be basis states. I missed a little bracket here. So this is sigma 1, state of spin 1. This is state of spin 2, right? So you already know that separation of variables, if there are independent variables, if they're truly independent, then overall quantum state will be their product. Later on we will see that it is a little more complicated than product. So, and there are 2 pairs of coefficients. So projections, spin 1 in state down, projection expansion coefficient that spin 1 is up, spin 2 down, spin 2 up. Formally, if we want to deal with this, it is an example of many particle wave function, right? Multi-electron wave function. We just do not focus on spatial component. We do not see how it moves in space. We look only on multi-electron aspects of the spin projection. So, what we all did in middle and high school algebra, we were opening brackets. Probably it's not wrong. Everyone was doing so. So 2 and 2 times 2 times 2, four terms. So first term corresponds to basis state that spin 1 is down and spin 2 is down. Second, spin 1 is down, spin 2 is up. Spin 1 is up, spin 2 is down. Both first and second are up, right? And instead of pulling these individual spin projections, it will be more reasonable to use expansion coefficients in front of each of these basis states. C1, C2, C3, C4. Okay? And now there is last thing to do, but it is not immediate and intuitive. So please let me know if the equation in the top line makes you happy and doesn't induce irritation. No one. Okay. If it may sound a little familiar. So what is it?
It's what we did last time.
No, in this class we never did it.
Oh.
Top line.
Oh, I'm sorry.
Top. The very top line.
Adding angular moment or adding spin together.
Yes, before adding spin together, what is the equation on the top?
Eigenvalue.
Eigenvalue of what?
The square of the spin operator.
Of total spin. Okay, so when one is looking for quantum eigenstates, most typically, and it is what we are always doing and will be doing in this course, is finding eigenstates of Hamiltonian operator of energy. But in some circumstances, when it is more comfortable and useful and there is a background to find eigenstates of other operators. For example, operator of total spin, or operator of spin projection, or operator of momentum. So, and sometimes the eigenstates of different operators are the same if the operators are commute. So for this multi-spin situation, there is a reason to find possible states of this two spin system as eigenstate of total spin operator. Eigenstates of total spin operator. Eigenstates of total spin, which will be like Sx total plus Sy total plus Sd total here squared. So since our basis consists of 4 states, this S capital S hat square operator will be 4x4 matrix. Okay? That one needs to diagonalize. And if one diagonalizes this matrix as a solution, as an eigenstates of this matrix, one would get possible eigenstates in which such system of multiple electrons may exist. And the lowest, if you combine it with assessing of energy, the one of the solutions, the lowest solution, will be the following. So coefficient 1 is 0, coefficient 4 is 0, and coefficients 2 and 3 are plus 1 over square root of 2 and minus 1 over square root of 2. So it comes as solution of total spin eigenstate, which we can together derive for another like hour. Okay, and now the only thing that has tiny connection to our course. Let's plug in the these coefficients here and see what happens. So this one disappears, and this one will be 1 square root of 2, and here will be minus 1 square root of 2. So electron 1 in function alpha, electron 2 in function beta, electron 1 in function beta, electron 2 in function alpha. So it is the same thing that we tried to use as two particles weighted determinant, antisymmetric wave function. So if you diagonalize total spin operator, the solution prompts us antisymmetric combination of individual orbitals. Okay? Done?
Okay.
Thank you for your patience. Next week I will be, please come to the scheduled rooms, and I will pop up the same way as Kurt popped up today. From the screen and
Sorry, my right's here, so I think.
that's okay, that's okay. Have a nice weekend.
You too. Have a great time in Sanibel.
Bye.
Take good pictures. Okay.